Well, hello, welcome back. We're in chapter 2 now, talking about atoms. So I mentioned this in the last lecture ever so briefly, but talking about atomic theory. And let me tell you about a technique called STM, or scanning tunneling microscopy. And so you can take this, and it's a tungsten tip on the surface, and it scans back and forth across the surface. And the idea is that when the piece of tungsten, kind of like shown there in the yellow balls there, when there's a signal, there's an electron nearby, you get a signal, and these images here, so just to the right, there's the one that has the green tops, and then the next one that has the Chinese symbols. Those are the atoms. And something to notice, though, the first image on the left, those are all very spherical, and the ones on the right, they look kind of like pimples. So atoms don't really look like pimples. They look like they're pretty spherical. And the reason for that is that if you see demonstrating there, that as the tip's scanning, so let me pretend my fist is a big atom. So it's scanning, and I'll put, here's my others on the side. So it scans over, comes over, scans again, and now an atom on the side can give a signal, and so that's why they look like the kind of pimply. I call it a pimple. There's probably a better word for it than that. It has a elongated edge. So, which is nice though, because we can actually see atoms. So imagine if I didn't have these pictures of atoms and I had to convince you that atoms are real. So, but we didn't have this technology in the 1970s, and atomic theory has been around since ancient Greece. So, and really strongly in mainstream since maybe the turn of the 20th century. So, right as we come around the year 1900. So, we obviously decided atoms were real before we could see them. So what happened? Well, let's look at this. So what is one of the things with atomic theory? And we talked about elements, we talked about mixtures and whatnot, and you have here the elements sodium and chlorine, and they can react to form sodium chloride. But when you do this chemical reaction, notice that 19.6 grams of sodium and chlorine react to form the same amount of product. So in a chemical reaction, atoms are exchanged, but the total mass does not change. So that's the thing with mass. Mass is conserved. And that's an illustration of this first law of conservation of mass. In any chemical or physical property, matter is conserved. And Lavoisier was the one that did this. He and his wife used to do lots of experiments to prove that things don't change in mass. Now the law of definite proportions. That tells you that for water, for instance, water is, well, we know it as H2O. We could break apart water, and we could find out that in the gas phase we would have two volumes of hydrogen gas to 1 part oxygen, or it would be 11% hydrogen by mass and 89% oxygen by mass, right? So that's the law of that's the law of definite proportions. Then there's the law of multiple proportions, where you have two or more elements can form different compounds, but with different set ratios. The example of that again is water. Hydrogen and oxygen can form water, H2O. It can also form hydrogen peroxide, H2O2. And they're very different substances, right? So if you drink water, it tastes good. You drink hydrogen peroxide, it's not going to be a good thing. You shouldn't do that. You throw a little bit of metal in water, not a whole lot happens. Throw certain metals into, well, I'll say a simple metal like iron or aluminum. Throw it in water, not a whole lot happens. Throw it in peroxide, there can be some interesting things that happen. So, well, don't do it. Even though please don't do it. And if you do it, don't cite this video as your encouragement, because I'm not. Okay, so Dalton took these ideas and he formed his atomic theory. And his atomic theory is that elements have a smallest unit called an atom, and compounds just have different atoms in them of different elements. And so the idea that then chemical reactions are exchanging of atoms. So that explains the conservation of mass, saying like, okay, we have sodium atoms, they're all the same, and we have chlorine atoms, they're all the same, and they form a new compound, sodium chloride, in the set ratio. And since all the atoms have the same mass and the products are made of the same atoms, that the mass doesn't change. And then, like I described for definite proportions and multiple proportions, talking about water and hydrogen peroxide, that was Dalton's argument. So where was he wrong? I said he was wrong in the last lecture. He's wrong because not all elements, or not all atoms are the same. I guess I should also talk about atom. Where did he come up with the idea? So let's say I got a piece of carbon. This is an Apple Pencil, but let's say it's a carbon rod. I snap it in half. And I take that and I snap it in half. And I keep on going. Oh, it's carbon, carbon. I'll get to a point where if I break it apart anymore, it will no longer be carbon. That's an atom of carbon. So it's the smallest unit of an element is an atom. Okay, so then we did some other experiments. This is all historical, so I don't want to do too much, but cathode rays came along, and these dealt with the presence of electrons. We did the Thomson ratio to see the amount of the deflection, and then the liquid drop model showed that there was positive charge, and then formed the plum pudding model of the atom. The plum pudding. So what the heck is plum pudding? Let me give you a better contemporary American example. It is the blueberry muffin model. So if you ever had a blueberry muffin, right? It's this big thing, and it's mostly muffin, but you have these blueberries in them every once in a while. Or maybe if you want some, how about a chocolate chip cookie model? So you have cookie and you have little tiny chocolate chips in there. The idea is that the atom was this big balloon of positive charge, and you had electrons floating in that big balloon of positive charge. That was a plum pudding model. So historically speaking, we had two models. We had Dalton's atomic theory that atoms were hard spheres. I guess I didn't mention that. Dalton thought atoms were hard spheres. And then we had the plum pudding model. And then Rutherford came along, and I do like this story, so I will tell it. Rutherford came along, and he said, you know what, I can take gold, I can pound it really, really thin, so I'm going to shoot radiation through this gold foil, and then I'm going to have a detector around the back of it, and I'm going to see what happens with the radiation. So actually, this is, from his setup, that's kind of like how a cheap smoke detector works. So you have a source of radiation. Alpha source in our case is some americium is typically used, and you shoot charged particles out, and well, the way a smoke detector works is the ionizing radiation will ionize smoke particles, and then it can hit a sensor, it'll set off the alarm. But let's go back to Rutherford's experiment. So he shot radiation towards gold foil, and he said, you know what, this would be easy. If it's Dalton's atomic theory, that's right, they're all hard spheres, they'll all bounce off. If the plum pudding model is right, it's going to go right through. So, and that's what he expected. But so most of them went through, but then some of them were deflected. And from this data, he came up with the idea of the atomic model. So specifically the nuclear model, that you have most of the mass in the center of the electron, or the center of the atom, and you have the electron cloud on the outside. So most of the space is occupied by electrons, and then the radiation will just fly through the electrons, but when it hits a dense nucleus, it gets hit away. And Rutherford was correct in this regards, and then we have these subatomic particles, so really, really tiny. And we have a proton, neutrons, and electrons, so we'll talk about these later. The nucleus of an atom is made of protons and neutrons. Protons are positively charged, neutrons have no charge. Electrons have a -1 charge. Well, relative charge. It's 1.6 times 10 to the minus 19 coulombs. So what's a coulomb? We talked about an amp. An ampere, you know what an amp is. You've probably heard of that. An amp is a coulomb per second. So, then, so an electron's charge is minus 1.6 times 10 to the minus 19 coulombs. To give an example, so 96,485 electrons equals the charge of 1 coulomb. So about 100,000-ish electrons, a little less, forms the charge of a coulomb. So, okay, so, and another thing you might notice is that a neutron weighs slightly more than a proton. Why is that? Well, it turns out that a neutron can and will decay into a proton and into an electron. So neutrons are ever slightly more massive. Okay, let's talk about the protons. So elements. So an element is the smallest unit of an element. I'm sorry, an atom is the smallest unit of an element, and we can describe them by the number of protons. So what defines a proton, or defines an element, are the number of protons. So the element carbon, for instance, has 6 protons. And if you look at this, we have the bottom number, often used to describe carbon, 6. That's the atomic number. It's also the number on the periodic table we'll show later. And then the top number of a nucleon there is the mass number. It's the number of protons plus the number of neutrons. And then I talked about isotopes. If you are a fan of the cartoon called The Simpsons, the baseball team in The Simpsons is called the Isotopes. So that's because there's a nuclear power plant and it's sponsored by, anyway, so there are lots of sciencey jokes in The Simpsons. So let's look at this. So carbon 12, number of protons. These are all elements. They all have 6 protons. This always makes me evil. Hoo-ha. Okay, neutrons. Carbon 12 has 12 protons plus neutrons and 6 protons. So 12 minus 6 is 6 neutrons. And electrons, atoms, definition of atom also includes that it's neutral. Ions are charged. Carbon will always have 6 electrons. A carbon ion can have different number, but a carbon atom is neutral. So carbon 13 here, next one over, there's 13 protons plus neutrons, and there's 6 protons. That means there are 7 neutrons here, and then still 6 electrons. Carbon 14, so 14 minus 6 is 8, and still has 6. So you can see here that the 3 common longer living isotopes for carbon have all same number of protons, all have 6 electrons, but the number of neutrons changes. Okay, so what about uranium-238? So normally in a classroom I would have this be a chem quiz, but here online you'll see these. I'm just going to go ahead and answer the question for you. If you want to pause the video and work on your own, then it's your call. The top number, 238, is the protons plus the neutrons. The bottom number is the number of protons. Take the top number minus the bottom number, and you get that one. Okay, so now we go on to talk about the periodic table. These are all the elements. So we have, this is incomplete, we have 118 now. But only about 92 of them are found naturally on Earth, and any appreciable quantity, it's much less than that. So, here they're all defined by the mass number, which is, or atomic number, the number of protons. So if an element has 1 proton, it is hydrogen. If it has 79 protons, it is gold. But that's probably not the first thing you noticed. You're probably like, what's going on with this funny shape? And we'll talk more about the funny shape later. But then you probably see this step ladder here. So what the heck is that? So the idea with this step ladder is everything here is a metal, and everything here is a non-metal. And then everything, what about over here along the line? Those are called semiconductors or metalloids, so metal-ish. kind of, sort of. But, and why did I include this over here? The periodic table actually looks like this. As blocks kind of look like this. That's what it would really look like. But it doesn't fit very nicely on an 8 by 8.5 by 11 sheet of paper. So we cut it off to make it closer to the golden ratio because we think it's pretty. So, but okay, going back to the periodic table. So let's talk about metals. So generally, properties of metals. Metals tend to conduct heat and electricity well. Non-metals tend to be insulators. Is that true for all metals and all non-metals? No. That's one thing with making generalizations in science, right? So carbon, for instance, carbon, at least the diamond form of carbon, is extremely good at heat conduction. So that's where the term ice came from. If you've heard diamond referred to as ice, or songs say, give me lots of ices, they mean diamonds. So why we call diamonds ice? Well, because if you touch them, they're cold. And as long as you touch them for a short bit of time. And it only works if the ambient temperature is lower than the body temperature. So, and that's true for most places, right? So diamonds were these magical rocks that whenever we touched them, they felt cold. So they must be magical properties. So we'll call them ice or magic ice. So also carbon graphite conducts electricity. DNA conducts electricity. It's all made of nonmetals. Well, at least, well, I shouldn't say there's at least the backbone of it is all nonmetals, right? So there are exceptions to the rule, but generally speaking, metals conduct electricity and heat. The electronic configuration is noble gases. Where are noble gases? They are the ones right here. Those are noble gases. And positive ions, so positive charge means electrons are lost. Negative ions means electrons are gained. So a positive ion is also referred to as a cation. If you can't remember that, think of the T as a plus sign. So let's go to this example here. Uranium-238 plus 6. How many electrons? Well, uranium has 92 protons, so it should have 92 electrons. The plus 6 means it has 6 fewer, so 6 are removed, 86. Oxygen minus 2. How many electrons? Oxygen has 8 protons as determined by the 8 in the lower left corner. Minus 2 means there's 2 extra ones, so 8 plus 2 is 10. All right, so, and a common hot topic today in science is astrobiology. We're looking for other life. And specifically, when we look for life, we look for carbon, hydrogen, oxygen, nitrogen. We just put it that way because it kind of says Chan. And that's something we can kind of say. And if you look at the composition of humans by mass, we are 65% oxygen, 18% carbon, 10% hydrogen, and 3% nitrogen. So, and if you look over here by number of atoms percents, we are 26% oxygen and 62% hydrogen. So we are often referred to as carbon-based life forms, but by mass we're mostly oxygen, and by atom we're mostly hydrogen. So why is this not surprising? Because we've got a lot of water in ourselves. We got lots of water, and so we're more than half water. That's where that comes from. We're more than half water because H2O, 2 hydrogens, 1 oxygen. But there's more than just life than water. There's so structures, there's cell membranes, proteins, DNA, RNA. That comes up with that. There's other things, so phosphorus, that's in DNA. There's a little bit more of iron, a little bit higher of iron. Calcium, there's a bit of calcium phosphate in our body. That's our bones, for instance. So but we're mostly, if you look at that, we are very much have a lot of carbon, hydrogen, oxygen, nitrogen in us. So that is what we are made of. Okay, let's move on and talk about the periodic table. So if you look at chlorine, there you see for chlorine. So 17, that's the number of protons, and then 35.45. So how are we getting 35.45? So what that is the terrestrial weighted average. So terrestrial here on Earth, and the mass of the isotopes. So there's chlorine 35 and chlorine 37. So I said chlorine 35, why does it weigh 34.97? And why does chlorine 37 have a mass of 36.97? So the answer for that is, if you ever heard of the equation E equals mc squared, so depending on which element it is, and if you look at the binding energy versus the mass number, the graph kind of looks like this. And the most stable isotope being iron, and then the lighter elements. So these lighter elements going up, the helium, actually it's even higher. Helium is particularly stable, helium-4. And then going up then, so the way so let me make another slight jump here. Stars burn hydrogen and other elements to get energy by nuclear fusion. That happens up until iron. After iron, it's endothermic. It takes energy away from the system. And when enough iron forms in the core of a star, the star can collapse rapidly. That's called a type 2A supernova. So, and then the implosion causes an explosion. So with the exception of hydrogen, helium, a little bit of lithium, maybe beryllium, the rest of us, that was formed in the Big Bang. The rest of the elements are formed in stars, and actually might be formed in other types of collisions, like collisions of other neutron stars. So that's for a different course, though. But I'm trying to explain why we have these fractional AMU, atomic mass units. It has to do with the amount of energy versus mass in each individual nucleon. So the amount of binding energy, which turns into mass, V equals mc squared. So, okay, but let me go back here. The atomic mass is then the mass ratio of the different masses of the isotopes. So let's look at copper here. Copper has 2 isotopes. So 62.9396, an abundance of 69.17%. And the second mass, 64.9278, with a natural abundance of 30.83%. So let's use this equation then. So the fraction of each isotope. So we have, and 69% is 0.6917 times the mass 64.9278 plus the fraction 31%. Oh wait, I have too many decimal points. I was just copying too earnestly with a mass of, oh, I got this wrong. Sorry. This one should go here. Like so. And then let me pause this. Okay, and so coming back here, I put in a calculator, and we have 4 sig figs from this measurement. So we have the mass of 63.55. And that is the number that's in the bottom of carbon. So that's the weighted average of the mass then for copper. Okay, so moving on, we have the next concept called the mole, and sometimes referred to as a chemist's dozen. So we sometimes use things, the bigger numbers to describe other numbers. So for instance, a gross. A gross is a dozen. If you want to buy pencils, so you can go and buy, if you order pencils, they sell them by the gross or the half gross. A gross is a dozen. Half gross is 6 dozen pencils. So we have this huge unit we use is the mole. And the mole is 6.02 times 10 to the 23rd. So that's 602 with 21 zeros after it. That's a lot. That's a big number. I should tell you 2 things. First of all, man, that's a huge number. The second thing to tell you is atoms are small. They're really, really small. So, but we'll go more and more in the mole concept later. But let's do some problems with this. Calculate the number of carbon atoms in 2.45 moles of copper, 2.45 moles of copper, that's copper, times then mole copper, actually no, I got it backwards, times by the Avogadro's number, 6.02 times 10 to the 23rd, atoms, copper, over mole copper. Next thing you're asking is, what the heck am I doing? This is something called dimensional analysis. So if I were to ask you, how many seconds are there in a year? Well, does anybody know how many seconds there are in a year? I don't off the top of my head. I can figure it out. So I can take 1 year, I can multiply it by 365 days in a year. And then I can say, oh, there's 24 hours in a day, and then there are 60 minutes in an hour times, and there's 60 seconds in a minute. And then I can notice that the years cancel, the days cancel, the hours cancel, the minutes cancel, and I'm off with seconds. And really, though, I'm just multiplying by 1. 365 days is the amount in a year. I mean, yeah, I know it's a little bit more than a quarter day more, right? The leap year, and then there's a little bit more after that. 24 hours in a day, well, at least that was true about 1980. It's a little longer now, you know, close enough. Minutes and seconds, those are pretty standard. But, right, so, but we're pretty much just multiplying by 1. And that's what we're doing here. We will notice then that the moles of copper will cancel. And okay, now we've put it in a calculator, and the answer then is going to be 1.47 times 10 to the 24 atoms copper. And something to note in my calculator, when I did that, I used this E button. Using that E button in your calculator, if you have a graphing calculator, make it much easier, or just a scientific calculator. So, okay. Question here is, how many oxygen atoms are in a half mole of oxygen? So this was meant to be a trick question because a half mole of O2, this bottom number means that there's 2 oxygen atoms, so a half mole of oxygen, O2, half mole of O2 oxygen actually has a full mole of oxygen atoms. So let's do some more calculations. So what amount of carbon contained in a 0.0265 gram pencil? So again, do dimensional analysis. Look at what you know. 0.265, this is our given, grams carbon. And now we want to get to moles carbon, and we can do that then. We can do that using dimensional analysis. So multiply this by 1. So mole carbon over 12.01. And this grid here, I use that grid because, well, for 2 reasons. It makes it easier for me to write on, and the other reason is because I have an engineering degree. I have a PhD in chemistry, but I have a chemical engineering degree as well, and we have line graph paper, so I just like doing it to keep things neat. And this one I'm not going to show the calculator since it's pretty easy. I'll just do this right now. 0.265 times 12.01. And I get 0.318 moles carbon. So, and again, this is dimensional analysis, and I'm trying to teach you how to approach problems, look at the given information, look at where you're going, and then fill in the different steps. So how many copper atoms are in a copper petty with a mass of 310 grams? So same as pure copper. So 3.1 grams copper. So mole copper, it was 35.55. Well, didn't we just do that as right? It's 35. Sorry, I'll make sure here. 63.55. So 63.55 grams copper. That's what a mole is, 63.55. And then another step, the mole, 6.02 times 10 to the 23rd Cu atoms per mole copper. So putting this in, I'm not going to do the calculation. I'm just going to talk while I do it because this one's pretty easy. So it's just 3.1 times, oh, actually I should do divide. Divide 63.55 times 0.02 E23. And from that we get 2.94 times 10 to 22 Cu atoms. And I had 3 sig figs from 3.1 grams. Actually, I think I will take a picture of this because I can illustrate a point. So, actually what I can do is I can do this. So, looking here, something to note there, and you're like, well, you're dividing and you're multiplying. How does it work? Well, with this one, this is dealing with order of operations. Where I see the mistakes with students is very frequently in order of operations. Here's the order of operations. The first thing here in red, what goes on in the parentheses happens first. Doesn't matter what it is, parentheses go first, and the most inner parentheses happen first. Then next thing that happens are exponents and logarithms. Then the third thing is multiplication and division, and then addition and subtraction. It always goes left to right. So meaning this computer, in my calculator as a computer, it's taking 3.1, it's dividing it by 63.55, and it's taking that answer and it's multiplying it by Avogadro's number. If you were to put parentheses in here, it would do 63.55 times Avogadro's number first, and then divide that by 3.1. So remember, our computers are smart, but they can only do what we tell them to. They're not smart enough to do anything except they tell them to. And chemistry right now, if you're tired of doing all this stuff, like, why can't we have a computer do this? Actually, right now, chemistry and chemistry problems are something that computers cannot do. Only humans can do it. We have some artificial intelligence. It can help fly planes. It can help diagnose people, generally speaking, but it can't really diagnose people. So we're not going to robot doctors yet. We're not going to have robots or artificial intelligence. Maybe robot, I mean artificial intelligence. We're not going to have AI doing chemistry homework yet. So you're stuck doing chemistry homework because humans right now are smarter than computers. It's a good thing. So, all right, so then how many oxygen atoms are there in 16 grams of oxygen? And then again, I'm trying to get you to think. 16 grams of oxygen is in fact a mole. So this is then that. So, okay. Well, I hope you've enjoyed today's lesson, and I will see you the next time.